Hello everyone! In the first part of the video What Electricity, we discussed three topics about magnetized wagons, macro and micro worlds relationship, and about micro items inclined to move from the place of excess to the place with scarcity. If you accidentally skipped first part, please watch it now and return back. We will use examples soon from the first part. Last topic of the previous video was about excess and scarcity. We discussed using example about airflow. There are also other similar natural phenomenon when surplus pushes towards scarcity. And electricity is one of such examples. But we need first to introduce several terms to understand what electricity is. From end-user perspective, electricity is surrounding us. Using a lamp, TV, computer, mobile phone and lots of other devices means that you use electricity natural phenomenon. Electricity brings energy so devices can work. Electrical energy is supplied by electric current. Likewise, certain energy named kinetic is supplied by river current. A river is strong to bring lots of things down with its stream. Even word current is the same for both processes. River current is actually a flow of water influenced by gravity forces. An electric current is a flow of electric charge. Remember electrons and positive ions from microworld discussed in the first part. They both have electric charge property and can flow, meaning travel, move through a matter. But how and where they need to flow? Are both electrons and ions, or maybe other particles, travel to bring electric current in action? Let's first answer the question where electric charge can flow. When we discussed tubes in Children's Museum, we need to realize that air inside the tube is a good place for matter to be moved from higher air pressure to lower air pressure. In the meantime, tube's plastic walls are impenetrable for the air. Same with electricity. There are some materials which are good for electric current, while others, in contrary, are definitely not good for that. Electrical conductor is a type of material which freely allows the flow of an electric current at least in one direction. So conductor is generally a good candidate for an electric current. Just for information, an electrical insulator, in contrary, is a material whose internal electric charge do not flow freely. In other words, insulator blocks electric current completely or high enough to a certain extent. Gases in usual conditions are not electrical conductors. Few liquids can be good electrical conductors. But in most cases, it's more convenient to use solid materials for carrying electricity. Electrical conductors, when they are solid materials, keep their structure on a micro level by atoms' nucleuses. Nucleuses are not moving freely. They stay in their places and preserve structure of the material in a form of lattice. But atoms of conductors are big, containing lots of electrons. And those electrons which move on the farthest orbits of their atoms, they have weaker attractive forces to their nucleuses, because of relatively high microdistance between each other. Such electrons can jump out from the orbit of their atoms and can move freely. As a result, electrons are the particles which carry electric charge in electrical conductors, in case conductors are solid materials. Metals are good reservoirs of electrons in close proximity to each other, ready to move freely at least in one direction, drifting around from atom to atom. Since electric charge is carried by electrons in solid materials, therefore materials made of metal are common electrical conductors, and they are widely used in electronic devices. When we use electricity in practice, we need to deliver our energy to particular devices, like electric bulbs, LEDs, light-emitting diodes used in flashlights, or any other electric devices. Conductors and metals in particular can be of any form, but it's more convenient to use certain paths for electricity to flow. Imagine that you burst an air balloon. High air pressure will be released in outside air, pushing balloon in potentially any direction, not controlled by you. But for example, tubes in Children's Museum are good for an airflow traveling inside them in predefined direction, keeping in mind that air is not going through tubes' plastic walls. Same way with electricity. It's more convenient to use metal wires, which are conductors, thin enough in diameter, and covered by plastic materials, which are insulators. That's how we can predictably control where electricity can travel and be delivered from electrical energy source to consuming devices like bulbs, LEDs, and so on. And what can be considered as a source of electrical energy? Actually, it's related to our topic from excess to scarcity from the first part, where we were talking about museum tubes with air movement from higher to lower pressure zones. We also discussed earlier that electric current is a flow of electric charge. In metal wires, it's a flow of electrons. And such electrons flow from a place of excess of free negatively charged electrons to a place of scarcity of electrons. It may be a place full of positively charged ions. So the source of electrical energy should always have pair of places, one with excess of electrons and another one with scarcity of electrons. You can think of the simplest example, the battery. Batteries always have two metal contacts named battery terminals. Positive terminal marked with plus sign and negative terminal marked with minus sign. I hope you can guess which terminal has a surplus of electrons in operational battery. By the way, the more electrons on the one side and the more positive ions on the other side, then the higher the difference in electrical potential between 2 points. And such difference is named voltage. 1.5 volts or 9 volts labels on a batteries, for example, are about quantitative measuring of voltage. The higher the number, the higher the difference in electrical potential between battery terminals. To have possibility for electrons to move from negatively charged to positively charged place of electrical energy source, we need to have a complete path for such flow. And we have another term for such a complete path, electric circuit. Electric circuit is a combination of consequently connected electrical components, including source of the electrical energy. The simplest example of such circuit is a battery connected by metal wires to LED lighting in a flashlights. So electric current in this case has started flowing from battery's negative terminal through wire, through LED, through another wire to positive terminal of the same battery. Historically, it conveniently happened that sources of electrical energy are compact enough and have both terminals close to each other. At least I never heard about battery terminals or other electrical energy sources terminals located miles away between each other. Therefore, sometimes you can see in some literature that electric circuit should have a closed loop, because electric current starts from one battery terminal and finishes to another terminal of the same battery, while terminals are in a close proximity to each other. I want to pay attention that for electric current it's important to have a voltage, difference in electrical potentials, surplus and deficit of electrons. And if you could have voltage miles apart, you still have electric current. What really might be important in closed loop terminology is to be sure that there are no breaks in electric circuit on the way. Because if you have a break in your circuit somewhere in the middle, there will be no voltage applied and no force for electrons to flow. That's how switches are used to switch devices on and off. They are actually connecting, making working electric circuit, so LED in a flashlight is very bright. Or disconnecting, breaking a circuit, so LED has no electricity coming through it, stopping lighting. Similar way as kids in children's museum can block off airflow by closing a tube somewhere in the middle, so air cannot move to the tube exit with the lower pressure anymore. One more thing to discuss. How fast does electricity travel? How is it correlated with the speed of electrons traveling in the wire? You probably heard that electricity travels at the speed of light, very, very fast. So your devices can be turned on near instantaneously even if the switch is thousands miles away. But funny part is that in the meantime individual electrons are usually moving with a speed of less than a millimeter per second. How these two things can coexist together? To imagine that better, let's remember our initial exercise with magnetized wagons from the first part, very previous video. Do you remember the whole chain of wagons started moving in a direction away from your locomotive? Exercise with magnetized wagons is an example of forces working at the same time between any two magnets lengthwise from the first till the last magnet, regardless how many magnets you have in between. Forces are working for each and every magnet in our chain all the way. And such chain can be theoretically miles long. Individual magnets can travel slowly enough, but overall flow can be seen all the way along, immediately at the beginning, any place in the middle, and at the very end. Example with magnets is not precise, but gives similar idea and visualization. Negatively charged electrons repel each other due to the nature of electric charges. Don't mix with magnetic fields though. Electrons start repelling each other from negative battery terminal with excess of electrons and push all freely moving electrons in our metal wire. Our metal wire is an electron reservoir, will be under electric charge force along the whole length of wire near instantaneously. All free electrons will be drifting in the direction from the negative battery terminal to positive battery terminal, repelling each other. If you have electric component or device at any place of the circuit, for example in incandescent lamp, electrons moving inside this device will make certain work. Lamp will produce heat and light. Hope you can understand the idea now better. As we were just talking about electron speeds, the more electrons, I mean number of electrons, can travel per second through the wire's boundary, the more work electricity can do. Such work can be measured in units called amperes. And actually electrical companies are charging you monthly based on consumed power directly proportionally related to amperes. The more electrons are marching through your electrical circuits in your house or apartment, more amperes and electrical power are consumed. The more you pay. Let me wrap this up using terms just mentioned. Electrical energy is supplied by electric current, a flow of electric charge, delivered by electrical circuit. Voltage is the difference in electrical potential between 2 points. Electrons are moving slowly but bring electric repelling forces along the whole length of electrical circuit near instantaneously. Number of electrons traveling through the wire's boundary do the actual electricity work, and it's measured in units called amperes. And the last topic to discuss in this video is about two types of electric current: direct current and alternate current. Electricity is produced on a special power plants where form of one energy is converted to electrical form. To make the electrical process economical, plants must be large and serve many customers. To serve many customers, electricity needs to be delivered. Electric power transmission is the process by which electrical energy is transmitted by electrical conductors to another location at a distance. Early in a history and in prior examples in this video, direct current was used. Direct current has a property that is always flow in one direction, from preliminary specified negative electric source of energy terminal towards positive terminal. It turned out that direct current is economically not good to be delivered to consumers at a large distance. 3 reasons are behind it. First is energy loss in conductors in general, appears as a heat. Second is energy loss in conductor with low voltage in particular. For safety purposes, consumers have low voltage. In the US, it's around 110 volts in houses. But less energy loss can be observed in case of transmitting higher voltages with tens or hundreds thousand volts, which are in turn not safe for human at all. And third is, for direct current system, there was no convenient means of changing voltage to achieve convenient energy transmission. Use high voltage between electrical plant and houses, and low voltage for domestic service inside houses. Solution was found to use alternating current instead of direct current, because a simple key device of the alternating current system, named transformer, was developed in 1886 for making convenient way of desired voltage change. Transformer uses basic laws of electricity and magnetism, which can be discussed in details in a separate videos about magnetism and electromagnetism. Thus, the basic limitation of electrical power transmission may be overcome. If the voltage of the generator in power plant is not sufficiently high for the economical transmission, a transformer can be used near generator to step up the voltage to the desired value for transmission. For transmission, a high voltage is used, and at the receiving end, another transformer steps the voltage down to the appropriate value. What makes current an alternating current? The main characteristics and difference is with the direction of the current around the circuit. In direct current, direction is always the same. Electrons always travel from negative terminal to positive terminal. In an alternating current, direction of the current reverses periodically. Electrons move one direction, then reverse direction and start moving back, then reverse back to initial direction, and so on. Imagine that we have two locomotives, one on each side. First, you move locomotive on the left side towards locomotive on the right side, repelling all chains of wagons to the right. In a moment, you stop moving locomotive on the left side and start moving locomotive on the right side in the opposite direction, repelling all chains of wagons now to the left. Once all your wagons return to the initial position, left locomotive starts moving all wagons to the right, and so on. A complete change of current between the same positions after moving one time back and forth can be named cycle. In the United States, electrical systems are designed to use 60 cycles per second. Number of cycles per second also named frequency. In Europe, 50 cycle frequency is used in electrical systems, by the way. Funny fact that frequencies below 50 cycles per second are undesirable for general use because electric lights have an objectional flicker. Of course, you need to have special energy source, power plant, which produces alternating current. Oversimplified, if you would think you have two wires going out of power generator, first wire will have increasing surplus of electrons, while second wire at the same time will have increasing deficit of electrons. Then, over a short period of time, the same first wire will start having increasing deficit of electrons, while the second wire will start having increasing surplus of electrons, and so on. It's simplified like flipping positive and negative terminals on the same two wires several times per second, 60 times in the US. Such changes are smooth over the time. Increasing and decreasing of electrons are going gradually, not immediately to their maximum values. Even though direction of an alternating current periodically changes over the time, it's still army of electrons moving back and forth, and energy of this army is able to make some work. For example, incandescent lamp in your home will produce heat and light if used. Actually, you have alternating current supplied in your home electricity outlets for all your lamps, laptops, refrigerators, amplifiers, and other electrical devices. That's enough for discussing in this video what electricity is. Let's wrap up what we discussed so far. We started with three notional examples in the first part of the video. First one was about magnetized wagons chain to show how one magnet can move the whole chain. Micro and macro worlds were discussed next, where we were talking about atoms, molecules, positive charge atoms center region called nucleus, and negatively charged electrons orbiting around nucleus. Same electric charges repel each other, and just in case we mentioned that electrons spin over its own axis brings magnet field, so electron acts like a tiny bar magnet as well. Electron has electric properties and also magnetic properties at a time. Third notion idea was about natural incline of moving from a place with excess to a place with scarcity, with an example of air tubes in museum with air pump bringing air movement in certain direction inside tubes. Then we moved to current, second part of the video. Next topic was about electricity itself. We introduced several terms, mentioned that electric current is a flow of electric charge delivered by an electric circuit. We mentioned electric conductors and insulators, metal wires as a good example of conductors used. Electrons are the electric charge flowing in a metal wires. Voltage was mentioned as the difference in electrical potential between 2 points. Regarding the speeds, electrons move slowly, just less than a millimeter per second, but bring electric repelling forces along the whole length of electrical circuit near instantaneously. Number of electrons traveling through the wire's boundary do the actual electricity work, and it's measured in units called amperes. And finally, we mentioned difference between direct and alternating current. We mentioned that due to energy loss, electric power transmission is effective at large distances only in case of using alternating current and high voltage. And it's become possible due to special key device named transformer, making convenient way of desired voltage change up and down. In alternating current, direction of the current reverses periodically. Number of two-way direction changes or cycles per second called frequency. We don't mind if any museum can implement locomotive and magnetized wagons to explain some magnetic and analogical electrical aspects of physics, or maybe even improve an experiment. No royalties needed by the author or company owns this video regarding this experiment, but referring to this video is mandatory. Museums can have funds and enough magnets, so we can mutually benefit from it by showing practical proof of our theoretical assumption. Thus, we have just answered to the main questions of this two-parts video. What the electricity is about. If this video allowed you to understand what is it about, you should be good to watch the very next video to find answers to the questions why you may need to learn this topic deeper, why it might be interesting and potentially applicable to you. Ready to watch the next video, Why Electricity? Then see you there!